Hi, everyone. My name is Piotr Teterwak. Thank you for watching this presentation. Today, I'm presenting Learning to Compose Superweights for Neural Parameter Allocation Search. This is work done at Boston University in collaboration with ETH Zurich. As we all know, model sizes are growing. Vision models, such as EvaClip, have exceeded 5 billion parameters, while large language models, such as switch transformers, have exceeded 1 trillion parameters. This creates big challenges. Models become difficult to store, and the training memory footprint makes it difficult to fit in the memory provided by GPUs. But parameter sharing, where parameters in one part of the network are tied to another part of the network, can help. They can decrease storage footprint, decrease the training memory footprint, and even act as a regularizer. For example, shared wide ResNets, introduced by Pedro Savarese and Michael Mayer in Learning Implicitly Recurrent CNNs Through Parameter Sharing in ICLR 2019, show reduced testing error on CIFAR 10 and 100 relative to their unshared vanilla counterparts. Prior work in parameter sharing can be divided into two groups: manual sharing and automatic sharing. In manual sharing, the user annotates which layers share weights, illustrated in this illustration where the layers which have the same colors share weights. Then layers which share weights are allocated a set of parameters. Those parameters are reshaped into templates, each of which is the same shape as the layer weights. Then layer weights are formed by linearly combining the templates with learnable alpha coefficients. Layers which share parameters use the same templates but different alpha coefficients, allowing for specialization. While manual sharing already confers benefits, automatic sharing eliminates the need for manual sharing annotations. Shapeshifter networks, introduced by Plummer et al. In Neural Parameter Allocation Search, ICLR 2022, clusters alpha coefficients after a short pre-training. Cluster membership is used to generate the sharing pattern, and the learned sharing pattern might look like this for a wide ResNet. While shapeshifter networks allow for sharing between layers of different shapes, this requires interpolation, such as bilinear upsampling. But bilinear upsampling can create artifacts, and this represents a limitation of the work. Another limitation is gradient conflicts. Prior work clusters alpha coefficients after a short pre-training directly in weight space. However, gradients can still be pointing in conflicting directions, resulting in optimization difficulties. This brings us to our work, SuperWeight networks. SuperWeight networks do not require warping for sharing between layers of different sizes and use gradient signals to learn cluster membership, minimizing gradient conflicts. We start with some definitions. First are the SuperWeight clusters themselves. These are learned groups of layers which share parameters. Then we have superweights, which are learned linear combinations of parameters. Then we have layer weights, which are tilings of superweights to construct layers. And finally, those layers are assembled into models, or in this case, a model ensemble. Let's start with the most important piece, creating superweight clusters. We start with an initial clustering based on layer depth. After a short pre-training, we compute all pairs gradient similarity for layers within a cluster. Then, using a priority queue, we merge layer pairs with sufficiently similar gradients and split layer pairs with conflicting gradients. This results in a final SuperWeight cluster assignment of layers. Once we have SuperWeight clusters, we allocate some parameters to each cluster and create templates team. Those templates are linearly combined with alpha coefficients. The sizes of the superweights are determined by layer sizes, as we'll see in another slide. For each layers, the superweights are tiled. For example, layer 3 is a tiling of the blue superweight and the green superweight. Notice the green superweight is sized to a small layer, while the blue superweight is sized to make up the difference in size between layer 2 and 3. Then the layers are assembled into models or ensembles of models, which can even have different architectures. A final note, in the first bit of training, alpha coefficients are tied. However, this is too restrictive, so we again use the threshold over the cosine similarity of gradients to untie alpha coefficients after some amount of training. We now present results for several settings. We start with sharing within a single network in the low parameter budget setting. For 1, 5, and 10% settings, we outperform prior state-of-the-art, which are shapeshifter networks, by a substantial amount on CIFAR 10, CIFAR 100, and ImageNet. Notably, over the baseline of slimming a standard network down to meet a parameter budget, we outperform by up to 4% on top 1 accuracy. We can also share parameters between members of an ensemble. In this scenario, we can compare to prior parameter-efficient ensembling methods such as MIMO and batch ensemble. The heterogeneous ensemble variant of our method, where the ensemble members are of different architectures, outperforms prior work on most metrics on CIFAR 10 and 100 with 36.5 million parameters. If we keep ensemble members the same architecture, but just add parameters to the templates, we can outperform even deep ensembles with 18% fewer parameters. Ensembling heterogeneous architectures also enables anytime inference. For higher latency restrictions, one can run the smaller members, and for lower restrictions, one can run the larger members, and one can also run several ensemble members together. The red and blue lines represent SuperWeight networks in their heterogeneous ensemble form, and which outperform prior work on CIFAR in terms of anytime inference. On the y-axis, we have accuracy, and on the x-axis, we have average inference time reported on a single P100 GPU. Since the red and blue lines are mostly above and to the left of the other lines which represent prior work, we're able to show that we outperform prior work. We note that SuperWeight networks are a general purpose parameter sharing method which happens to enable anytime inference, whilst prior work is specially designed for anytime inference. In summary, we develop SuperWeight networks which improve on prior parameter sharing works by minimizing parameter warping and minimizing gradient conflicts. We show SuperWeight networks can enable effective sharing between layers within and between models. And we show accuracy improvements on CIFAR 10 and 100 and ImageNet datasets on a single network, efficient ensemble, and anytime inference settings. Thank you.